Hello and welcome everybody for this presentation on everything that's new and cool in the latest release of the Xpress Solver family version 9.0. I will now retract to the top right of this screen and see you at the end of this video. As you might be aware, FICO Xpress optimization consists of various components, all built on top of each other and nicely integrated within each other. For your application in your company or institution, you might enter the stack that we see here at different levels. You might use one of our business solutions or directly work with our software components. Like you might develop your models in Express Workbench, our in-house IDE for optimization, and deploy them via Insight to cooperate with your colleagues on the cloud. And probably you develop your models in Moselle or in Python, or you use the solver via one of our many APIs in various programming languages. And speaking of the solver, this is where I work down here in the deepest, the lilac level on the heart of Express, the solver core. And in the next round about 45 minutes, I would like to tell you what news and new features there are to make this heart beating more vigorous than ever. Us developers in the solver team have three main drivers: performance, features, and robustness. These are the things that we work on in each and every release. First and foremost, we strive to make our wide variety of optimization algorithms and solvers for various types of optimization problems faster and faster with every release. And secondly, we want to make your life more convenient and open new optimization applications by offering new modeling capabilities, enhancing analysis tools, and other valuable features. And finally, we always aim to further improve our solver's numerical robustness, with Express already being the most deterministic and probably the most numerically robust solver. In this presentation, I will describe the improvements made to FICO Xpress during the past release cycle of 6 months. And the focus of this release were two massive new features for enabling you to solve new types of optimization problems. One of these features, the global solver, is so big that it did not only justify jumping from an 8.14 release version to 9.0, but this one also deserves its own video. Still, we could put a lot of time and effort into our MIP performance development to present you an Express solver that is faster than ever before. And to this end, we worked on all aspects of MIP solving: cutting, branching, heuristics, pre-solving, and I brought at least one highlight from each of these fields today. And afterwards, we will discuss all the API changes, and there are quite a few, for two reasons, and one of which is Express Global, our new solver that extends the nonlinear solver technology that we had in Express for over a decade now, and it builds on our existing MIP solver and is able to find provably globally optimal solutions to general NLPs and MNLPs, and yes, including non-convex, and yes, including almost all kinds of nonlinearities you can imagine. However, no user functions. Nice bit about building on our existing nonlinear technology is that you do not have to change much if you are already a user of Express Nonlinear. You can simply keep your existing modeling and processing mechanisms in place and set one additional control. It did, however, require to change some of the API naming conventions, but we will come back to this towards the end of the presentation. And if global optimization sounds interesting to you, do not hesitate to write us under Express Global Beta at fico.com and ask for an evaluation license. And for today, I will leave it with this super condensed overview slide here. However, there's a whole release video of its own, which should be linked in a YouTube card and will also be linked at the end of the video. Okay, that's enough global for now. Let's talk about multi-objective optimization. So, what exactly is multi-objective? Well, who would have guessed optimization with more than one objective? Typically, objectives that are conflicting with each other. Minimizing cost while maximizing comfort, for example, or maximizing potential gain while minimizing risk. Maximizing performance while minimizing consumption. All of these sound a bit too good to be true, well, because they are. When you improve one of the objectives, you typically degrade the other one in all these examples. And the set of solutions that can arguably be considered optimal when you give different importances, and the trade-off between the two is often referred to as the Pareto frontier. It includes all solutions where no improvement in one solution is possible with degrading the other objective. As extreme cases, solutions that fully optimize one of the objectives, more precisely among all those optimal for one objective, the one with the best value for the other. We should say here that sometimes multi-objective optimization is referred to as computing the whole Pareto frontier, which might be prohibitively large, and this is not what Xpress does. It will compute you one Pareto optimal solution. I should stress that this new feature covers all existing types of optimization problems, so your multi-objective problems can be continuous or mixed integer, they can be linear, quadratic, nonlinear, whatever you want. They can have special MIP entities like sources or semi-continuous variables, right, you name it. And multi-objective is available through all APIs. So there are two major ways how multi-objective can be realized, and often you will find research papers or also software implementations that only support one of them. But we thought, hey, let's do both. The first approach to solving multi-objective problems in a single shot is blending. This leaves the user the choice to specify the objectives against each other and assigning each of them an importance. So I should probably add that while I always use two objectives in my examples, the term multi is there for a reason. So of course you can have arbitrarily many objectives at the same time. Anyhow, in blending you assign a weight to each of them, like I want more tangerines in my smoothie or more bananas, and then they are all blended together and the optimization is done with respect to the blended objectives. This would admittedly not be too hard to do externally, but still this gives an easy way to let the optimizer manage all your objectives and just play with the weights. And when you save and look at your problems, the contextual information that this is indeed a multi-objective problem gets preserved. So this is all nice. Next approach to multi-objective is hierarchical, or sometimes also called lexicographic optimization. So this assumes that the user can provide a strict ordering of the objectives, like grapefruit first, then oranges, then lemons, then limes. And if you know what the fifth fruit here is, please let me know in the comments. And Xpress will then solve for each of the objectives individually, but always restrict the solution space to the set of problems that is optimal with respect to all previous objectives in order, of course. So the optimality condition of one becomes a constraint of the next one, like we see here on the slide. And yeah, always in a loop until we have solved the problem for all objectives. So in our picture 2 slides ago, this would have given one of the extreme point solutions. And as I said, lexicographic optimization is realized via the user setting priorities. And just in case you wondered, yes, of course, you can mix and match the two approaches and assign priorities and weights at the same time. And Xpress will then automatically blend together those objectives with the same priority. And as before, there will be one solved per priority. And of course, to conduct multiple solved of a MIP problem, you first need, you name it, a good MIP solver. So let's dive into this and see what new performance improvements we have there. So let's start with the big one, cutting. Mixed integer rounding cuts are one of the most important cut families. They have been first described in 1990, and Xpress separates mere cuts, mixed integer rounding cuts, implementing a heuristic strategy inspired by the seminal paper of Marchand and Woolsey from 2001. So the principal idea of mixed integer rounding is to aggregate both in a heuristic fashion and then apply a disjunctive argument as it is shown on the right. So assume you want to cut off the tiny red triangle that you see here from a relaxation set that's defined only by a single linear constraint, this number 1 here, and the bound of the variable 2. So by rounding up and down the fractional value b, assuming that the variable has to be integer, you get these two new bounds here, 3 and 4. And as you know, simply due to inequality, one of them has to hold. So that means that you can combine the green inequality here, the MIR cut, either from 1 and 3 or from 2 and 4. And since this green inequality holds for both parts of the disjunction, it is the valid inequality for the overall problem. And this is the MIR cut, the MIR cut. While MIR cut, as the name suggests, work for mixed integer inequalities, but also for pure integer problems, category cuts, on the other hand, only work for pure integer-based inequalities. And again, they are created by aggregating different rows, such that there is a fractional right-hand side, and then applying 2 rounds of rounding arguments directly on this row. So first, all fractional coefficients on the left-hand side of the aggregation get rounded down, and the fractional right-hand side gets rounded down, and this is your category cut. I used to post a YouTube Shorts video on this earlier this year. So, like for MIR cuts, the important question is, what are good aggregations? So, a strengthening of classical category cuts are the so-called strong category cuts proposed by Litchford and Lodi. Unlike CG cuts, category cuts, no domination relationship between MIR and strong CG is known. So for the same base inequality, either of them can be better. So what we do now is to simply separate both the MIR cut and a strong category cut whenever appropriate, hence whenever the mere aggregation is pure integer, and then just choosing the better of the two to add to the problem, or rather to the cut pool. And this gives a nice performance improvement on hard MIP problems. Okay, our next cutting project are FICO cuts. This time the news is not about a specific cutting procedure or how to select cuts, but the news is where they are separated from, namely neither from the original constraints nor from the tabular rows or some ad hoc aggregations as we just saw, but from so-called FICO spoofs. So what are FICO spoofs? While running a branch and bound search, nodes will get pruned all the time. Essentially, all leaves that did not deliver a new incumbent get pruned. There are 2 reasons why a node can get pruned. Either node preserving detected the current subproblem to be infeasible, and this is not relevant for this particular slide, or the LP relaxation of the current subproblem is infeasible. So in the latter case, you can expect the infeasibility proof from the LP solver. And this infeasibility proof, called the FICO proof, is a set of multipliers on the original constraint that could gather with the local bounds given unfulfillable constraints. So you aggregate constraints to get another feasible, but locally invalid constraint. So yeah, together with the global bounds, this aggregation is valid. And yeah, since you are just adding up valid constraints, this gives another valid yet redundant constraint. So you can use the FICO proof to derive further information about the problem. And so far, it was mainly used for deriving bound tightenings by propagating this valid but redundant constraint. But now in Xpress 0, we will additionally also separate cuts from such FICO proofs. And the impact is admittedly moderate, but measurable and positive. So we have already talked about disjunctions for cuttings, as this is at the heart of many cutting plane algorithms, and lift and project, and likewise Montgomery mixed integer cuts, both use disjunctions on individual variables to generate cuts. And while theoretically possible, practically you will never cut for more general disjunctions. Well, if you are working with indicator constraints, however, there is a very natural way to impose a more general disjunction, and that involves the indicated constraint. Assume y is your indicator variable. Obviously, there are still the trivial disjunctions on the variable itself, y0 or y1. And whenever this variable y is fractional, we would prefer that simple disjunction for cutting. However, for an indicator constraint, you can also get into the situation that your LP relaxation solution sets your indicator variable to the value that will force the indicated constraint to hold. And at the same time, that indicator constraint is violated because it's not part of the LP. So note, by the way, that here in this example on the slide, slightly unusually, 0 is the value which enforces the constraint, and this is mainly for the last line of the slide to become less cumbersome. So anyhow, so if both your indicator variable is at the indicating bound, but the indicated constraint is violated, well, then you can cut or also branch under the junctions that either your indicator variable y has to change bounds or your indicated constraint has to hold, which is more simply expressed by using a slack variable for that constraint. Once you impose that disjunction, you can simply throw your whole machinery of disjunctive cutting on it. This is one of those projects which only affect a few models, namely those with indicator constraints, but on these models, it does a lot. On hard models with indicators, we saw a speed up of about 50%. Okay, let's continue with branching. The main branching strategy in Xpress is reliability branching, which combines so-called pseudo-cost branching and strong branching. Strong branching is a very precise but expensive evaluation of branching candidates where you tentatively fix each candidate to each of the possible branching values and solve the resulting LP, at least for a couple of iterations. Like in the tiny example here, 2 fractional variables give you 4 strong branches with 4 different objective changes from which you decide on which of the 2 variables you want to branch. You do this only for the first couple of times you evaluate that variable in some node, and afterwards you will use the so-called history costs, which simply average all effects you ever saw from branching on that variable. And it is this magic the first couple of times for the expensive full evaluation that we played around with in the last release. This will now typically allow for more strong branching in the beginning of the search to get a better kickoff for the branching bound, and our limits will be dynamically adjusted depending on the real computational effort of strong branching. And furthermore, we significantly improved our branching for highly degenerate objective functions. If you are one of those sneaky users solving MIPs without an objective, this one might be interesting for you. We would still apply some limited strong branching, and that is curious because it can obviously not help with the branching decision. However, what it can still do is helping to fix variables. The most important bit, however, was that we now make better use of conflict scores. Those are measures gained from infeasible nodes, similar to the FICO proofs I spoke about earlier. And the impact of that change is speed up of more than a factor of 2 for such highly degenerate problems. But given that those are rare, this boils down to only a 2% overall change in our benchmark set because of so few problems being affected. Okay, let's now switch topics and talk about pre-serving. In this case, a technique we call configuration pre-serving. This is motivated by a transport network planning problem where there's only few configurations of timetable frequencies that you can use, but these can come in form of many different train lines. And this leads to a very long binary row with only few different coefficients. And the example here on the slide is really an understatement. Often you have hundreds of variables with only 3 or 4 different coefficients. And this pre-serving operation then enumerates the maximal configurations for such a row, where each set of variables from one time is understood as one entity, essentially. You then introduce an extended formulation with new variables that represent a choice of one such configuration. And this reformulation is equivalent, but usually much tighter. Consider our example here. We only have 2 different coefficients, 7 and 13, but each of them a couple of times. There is only 2 fundamentally different ways to fulfill these constraints. Either set up to 3 7 variables to 1, or set 1 certain variable to 1, and at most one of the others. So we then introduce a variable set 1 that represents the first configuration, and a variable set 2 that encodes the second one, enforcing that exactly one of them is chosen and ensure that the right number of variable choices is allowed. So the second set of inequalities can then replace the first one. There's a few other minor things we did in pre-solving, like extend our graph-induced probing for chains of precedent constraint by the case that you have non-binary precedences, or have an improved detection of semi-continuous structures in the MIP model. And depending on the impact on overall model size, we would either formulate such structures as semi-continuous directly or via a linear reformulation. We improved our lifting procedure for cleat cuts, and when you are working with general constraints, you might now see a better dual pre-solving for absolute value constraints. The last improvement for our MIP solver comes from the heuristic side and uses a brand new technique that has only been introduced this year at the MIP workshop at Dymex. The feasibility jump heuristic. Have I heard a similar name before? Anyhow, the feasibility jump heuristic is an LP3 heuristic for MIP, hence it operates directly on the set of constraints and does not need a relaxation solution or even a basis to work with. It is a randomized local search that uses a Lagrangian approach to minimize the total sum of violations. And their weights are applied to more and more punished violations on roads which you have not seen feasible for quite some time. And in between, the heuristic does individual variable flips to improve the violation, plus random flips to escape from local minima. And this is only implemented for pure integer problems and only used to find a first feasible start solution. And the special bit is that it runs in parallel to the root cut loop on multiple threads, with each thread using a different configuration of the heuristic. And the sequence of the heuristic could look like in the picture on the right, where you see how it locally jumps from point to point until reaching the feasible region. Okay, so far for the scientific part. That was a lot of content. Let's now get into the technical part, API changes. And folks, this is a major release, so there are quite a few of them. First of all, we took the chance to remove some obsolete controls and attributes. Most of them were quite exotic, but one that I would like to point out is your strategy. These in the future use your emphasis, which can be used the same way if you want to disable heuristics, and is much better in enabling an aggressive heuristic strategy. There are a few other controls and attributes which have been newly marked as obsolete, and you will from now on get a compile time warning when you're using one of them. Also, calling an API function at a place where you really should not will give you an error, like trying to add a cut when the heuristic found a solution in a context outside the current node. So I hope this will not affect any one of you anyway, but still. On the brighter side, there is now a function to directly map the solution from the pre-solved space back to the original space, a feature that has been requested multiple times, and the dedicated callback called only once after the initial AP of a node has been solved, but before any internal cuts or heuristics. Speaking about long requested features, boy, it has been about time to do something about our timing. Firstly, all timing-related attributes and controls now use double precision and not full integer seconds anymore. Like you can set a time limit of 1.5 seconds and tell whether for one instance the first solution has been found after 0.1 and for the other after 0.75 seconds. And secondly, we got rid of that anachronistic behavior that you have to set a time limit as a negative value by setting the responsible control, max time, to a positive value took a different meaning. Hence, we introduced two new controls, each of them taking over one of the meanings and each taking non-negative inputs. The new double control time limit takes over the meaning that a negative max time had so far. Setting it to, for example, time limit equals 60 means stop the solver after 1 minute, 60 seconds, no matter what, which is what 95% of the users want, a strict time limit. Control sole time limit, however, takes the meaning that a positive max time had so far. The solver will only stop at that limit when it already has a solution. Note that you can now mix and match those two controls. For example, you can tell the solver to stop after 10 minutes if it already has a solution, but terminate the search after half an hour the latest, which has not been possible before. So in the course of these changes, the old max time now got deprecated, and you can still use it, but might get a warning and it might get removed somewhere in the future. And the same holds for XSLP max time. So XSLP now also uses the optimizer time limit unification A, and XSLP max time, the specific SLP control, has been deprecated. A few attributes and controls changed their type now from int to double, but not their meaning, mainly because there were no oddities with negative values. And we recommend changing the access to them to the corresponding double functions. You can, however, still use the old integer functions. Expect values to be rounded, obviously, for the getters. Next on the list is a lot of new API that is agnostic to the problem type. You can now load a problem and just tell the optimizer to optimize without having to specify the problem type for optimization. And to get the solution afterwards, the objective value and so on. And the optimizer will just use the problem type that is most appropriate from the context. Like if you read in a problem with only linear constraints, but integer variables, Xpress Optimize will solve it as a MIP. And if you call get solution after the solve has finished, it will give you the best MIP solution. Note that inside callbacks, it might be less clear what the intended behavior of, for example, get solution is. Would you want the node AP solution or the current incumbent MIP solution? And hence you still have to use the dedicated functions there if you are a callback user. There are also generic attributes, solve status, which refers to the optimization process per se, the status of the algorithm, has it failed, has it been completed, and so on. And Sol status, which refers to the status of the final solution, or rather the result of the mathematical optimization problem. Is it feasible, optimal, has it been proven infeasible or unbounded? And as a side note, you can still use the old functions and attributes. We rather decided for doing something universal here and against introducing yet another dedicated set of functions, attributes, and so on for the global MIP solver. Speaking of global, some of our naming schemes fell directly onto our feet when starting the global solver development. You might be aware that in Express we used the term global entities to summarize integer variables, sources, semi-continuous, and so on. Anything that makes a linear problem branchable, disconnected, and be hard, however you want to call it. But the search process, hence the branch and bound plus the cutting and heuristics, we also use the collective terms of global search for this. So this is a nice take until you develop a global solver, and this naming might lead to some confusion. Hence, we bit about it here and we named everything from the non-global solver API that had the term global in it to something that says MIP or MIP entities or tree. So also there are some equivalent changes in the logs, for example, after reading a problem. And all those functions still lurk around as deprecated and they just forward to the renamed functions, but we recommend to update. And finally, the function Express Global, which has been deprecated for years, by the way, got removed. So you see, there are quite some changes. Of course, they are all listed in the release notes, and we recommend to take a little time after installing 9.0 to check whether you use any of the affected functions. And we are, of course, always there to answer questions, for example, in our community forum. And also be reminded that most of the stuff that I talked about is introducing new API by deprecating the old one. Hence, nothing dramatic will happen if you miss to replace one call of a deprecated function. Last slide for API. In the process of making Express Global happen, we also got a tighter integration of the optimizer and XSLP. Again, a couple of functions have been renamed, and XSLP specific controls and attributes can be requested through the corresponding Xpress functions now. This is mainly for people starting new projects with Express, that they have in one unified API. For existing users, we still maintain the old XSLT API for backwards compatibility. Okay, some more assorted news. We have some changes in our MIP solvers. Our private syntax does now use a different perturbation scheme, which makes it about 10% faster and less prone to cycling. This also affects MIP users with numerically challenging problems, because the primary syntax is used as a fallback, as a cleanup procedure in MIP solving when dual syntax gets into troubles. And here on the right, we see an illustration of a problem that shows both primal and dual degeneracy, while of course syntax would have no issues solving this problem here. We would most likely see some zero step length pivots around here, where a vertex is overdefined, and certainly zero valued basic variables and reduced costs in the final solution because there are alternative optima. So yeah, this is because the optimum is not unique and the vertices are overdetermined. So for our users with fancy AVX 512 machines, we got a nice speed up in the FTON procedure of the syntax algorithm. And for our barrier users, we got a nice speed up from various different projects on crossover. And as already announced last time, all our algorithms are available on Linux ARM machines, more specifically the Graviton instances on AWS, now are also officially tested on Graviton 3. And reminder, yes, it is true, you will have save file compatibility between Windows, Mac, Linux x86 and Linux Graviton, and solution path consistency. This is great for all our partners, OEMs, everyone who has to work with clients and that use Express themselves. So because this feature, path consistency, makes reproducibility so much easier. So you can see what a user got on, say, a 64-core ARM machine on your 8-core Windows laptop, for example. So we did some work of improving performance on Graviton. That is, in Barrier, you can exploit the CPU-specific instruction sets to get about 10% improvement, and some additional compiler optimizations made the code some 5% faster overall. And yeah, just as a number, we measured that the speed up of Graviton 3 versus Graviton 2 with the same binary with an average of 40% and around 50% for hard instances. Quite nice for Graviton users. As I said, performance. Yep, finally, the most interesting part of every release presentation, performance numbers. A year ago, we released Express 8.13. This table compares our new 9.0 release against 8.13. It's the typical year-on-year improvement table that I always show in these videos. These are numbers on our benchmark sets that consists of a mix of public and client instances. And client instances are sampled to avoid any type to dominate the benchmark. Our MIP evaluation particularly is split into two sets: the benchmark set, for which we measure time to optimality, and the PDI set, which mainly consists of unsolvable models for which we measure the prime dual integral. This is also why the 100 greater 100 second column does not exist for the PDI set, because almost every instance would fall into this category. And looking at performance, we can see improvements in the individual MIP solvers and a nice 10% improvement for concurrent. Conversely, relevant improvements are shown by the MIP solver, both in the number of solved problems as well in the as in the average runtime performance. So yeah, this is certainly the highlight of the table here. Our MIP solver for more challenging problems is now about 20% faster than a year ago, and across all instances, which include some that are trivial to solve and will be solved by the initial LP, the overall speedup is still about 10%. And note that this benchmark set consists of 1,113 instances, each solved in 5 permitted versions, such that we get a total of 5,560 measurements to draw these mean values from. Okay, we are close to the end, and I would like to point out the Xpress Best Paper Award. This is an academic award that honors great scientifically valuable publications that use FICO Xpress. This can be a paper in one of the well-known OR, MS, or optimization journals, but also a paper that is published in a thoroughly reviewed conference proceedings. It can be on solving new types of problems or developing new application-specific algorithms that solve optimization subproblems via Xpress, or it can be a paper on new mathematical optimization methods based on an Express callback implementation, or really all other imaginable research where using Express optimization products played a significant role. The authors of the winning paper will be awarded a prize of $1,500, and for the first edition of the award, all papers will qualify that are published within the years 2021 and 2022, and you need to submit your paper by the end of January. If the deadline is too close, consider the next year's edition, for which your paper needs to be published by the end of 2023. So if you have any questions, you can send them either to the named email address, or I will also be happy to answer them. Finally, there will be an interesting workshop in Berlin next year, where FICO is the main sponsor, and my colleague Susanne and I are two of the main organizers. And the Europe Practitioners Forum is a meeting point for people from all different industries that use optimization and other OR tools. And the topic of this meeting will be OR as a resilient technology, or also known as lessons learned from the various crises of the recent years, be it the pandemic, the war, the energy crisis. Consequently, there will be speakers from a large supply chain company, a speaker from Europe's largest gas network provider, and a presentation on nurse scheduling, someone from finance, all people from practice. So register for free for this event. Send your abstracts until mid-January if you want to contribute to talk, and come to Berlin in April. This brings us to the end of the presentation. Thanks a lot for your attention, and let me point out our community page where you can get academic licenses for free, and you will also find a forum to ask any questions there. Let me also point out our release presentation for FICO Xpress Global, our new global solver with all details on its implementation and use cases. Thank you and goodbye. Happy holidays.